Namaste. Hope you are doing well. So today, or rather in this video today, we will be looking at the kind of mind traps that we can fall into while solving certain kinds of mathematical problems or hey, problems in life as well. So this would be slightly technical perhaps, but give it a minute. You have two variables, two random variables, and it said that they are random under some other variable m, and you are told to find the probability of something happening to one of them, given that you already know that something had happened to one of them before. Now, interestingly, we can start thinking in this direction that, okay, these are random, which means they don't depend on each other. They are independent. So what it means is this thing doesn't affect this. It's a trick question. And actually, this doesn't matter. The question is completely about this. So the question makers wanted to confuse me by giving this, but actually it's random. So yeah, life is easy. Or is it? No, life is easy, given that we don't complicate it ourselves. So is this what's happening? The question is presented in such a way that perhaps, uh, and given that usually questions have this nature of becoming tricky sometimes, so we often expect tricky questions, and maybe it can feel like this kind of question is a tricky setup, whereas the actual question is only this. And the question makers wanted me to waste my time thinking about this thing, but it's not relevant. And the essentially the mind trap over here is that there is no need for new information to be taken into account in the form of this given to us, or we already know everything marginally, so we have to proceed with the marginal one. There's no need to take new information into account. That is the mind trap over here, and that's so because yeah, here's the mind fix. They are random, but they are random once they are fixed upon a certain variable m. And this is where it may seem not intuitive at all. And there are some times when math seems very intuitive, but when it doesn't, when we are in doubt, notations can really help us understand what's happening. Because at least to me, if before preparing for this video, this thing was very much indicative of the fact that they must be random in general. It could be a competitive question tactic of throwing in deliberate things to confuse you, but there is more nuance to it. Let's see. So this over here, we are going to see the probability calculation using the law of total probability, and the other law is the multiplicative rule. Feel free to look them up. That is what has been used. These two have been used to break down this into this thing that you see. That and for sake of simplicity, suppose this random variable m takes two values. It's not degenerate. It doesn't take just one value. It takes two values, m1 and m2, and conditioning based on the way it takes two values, we can condition the probabilities. And similarly, we find the same for this as well. Now, two random variables are independent if the joint probability is equal to the product of the marginals, right? So that is what we are trying to do over here. We have the marginals over here, and we also look at the joint probability. We do the same multiplicative rule and law of total probability thing, wherein we have m taking two values for the sake of simplicity of illustration, and based on the two values that m takes, we can break the probability, the joint probability into this. And when we expand it further, now is the time when we use this. T1 and T2 are random under M. So they are over here conditioned under M, particular values of M. So these two are independent over here right now, and they can be hence broken like this and this, or in this case also it can be broken like this and this. And once they are broken, because under this particular variable m, they are random, it means they are independent, not just independent, they are identical as well. So this probability is the same as this probability, and hence it becomes same, so it's squared. And similarly over here it's same, so it's squared. And I hope now we see that why in general this thing is not equal to this thing multiplied by this thing. Because again, if it's not clear still, think about this. You have uh, this probability, and this is going to be exactly the same as this because they are identical under the values that m takes. So you have something like a pm1 and this thing under m2. You have this, and the same thing is over here, so this is the whole square of this. Whereas this thing is more like a m1 square pm1 plus a m2 square pm2, where am1 is this probability, and am2 in all these situations is this probability. So this is, these two things are in general not equal, and you guys from your end can do a little bit more uh, expansion and sort of take everything on one side and see when is the situation when they are exactly equal. But in general we can see they are not equal, and this sort of looking at the notation helps us get the conviction that yes, they are having some dependence. Even though the question was in a way, yeah, it was tricky to perhaps make you feel that they are independent, but they are independent only when they are fixed, conditioned under another random variable. So it's a very interesting insight. Two random variables may be independent when there is another third variable in the picture. But in general, if there is, we don't have the guarantee of the pivoting of that third variable, in this case it's m, they may not be necessarily independent. So I hope you found it interesting. A lot of technicalities and a kind of mind trap which has a philosophical connotation as well. We think we know everything, or we think we don't need to incorporate new information, but more often than not we don't know everything and we have to incorporate new information coming to us. Growth mindset. So yeah, let's see whatever video you see next, and take care. Hare Krishna.